That sound, it's not a trick of the ear, not some digital artifact from a distant satellite, nor the whisper of static across a radio band. That sound is the collision of two black holes, each 30 times the mass of our Sun. It happened 1.3 billion years ago, and the energy released in that final fraction of a second was more powerful than all the stars in the observable universe combined. We didn't see it. We heard it. For all of human history, our journey into the cosmos was a silent visual quest. We built ever larger telescopes, reaching out with our eyes to the farthest corners of creation, mapping galaxies, charting stars, and tracing the faint ancient glow of the Big Bang itself. We were explorers of light, interpreters of images, deciphering the universe through its radiant brilliance. But imagine if you could only ever see the world, never truly hear it. Imagine the symphony of a bustling city, the gentle rustle of leaves, the thunder of a storm, all rendered utterly mute. That's how we experienced the universe for millennia. We were, in essence, deaf to the cosmos. Our understanding, though profound in its visual scope, was fundamentally incomplete. Then, on September 14, 2015, something shifted deep within the fabric of our perception. On that day, humanity finally grew ears. We gained a brand new sense, a profound new way to perceive the universe around us. We learned to listen, and the very first sound we heard was that incredible rising chirp, the death rattle of two cosmic titans merging in an event so cataclysmic it warped the very essence of existence itself. This wasn't just another scientific discovery. It was a sensory revolution, an expansion of our consciousness, allowing us to finally perceive the universe in its full symphonic grandeur. To understand what we're now listening to, we first have to wrap our minds around one of the most abstract and mind-bending concepts in all of physics, spacetime. Imagine, if you will, that the universe isn't just a vast, empty stage where events unfold. Instead, think of it as an intricate, flexible tapestry, a four-dimensional sheet woven from 3 dimensions of space and 1 dimension of time. This isn't just an analogy. It's a fundamental reality, described by Albert Einstein's general theory of relativity, published over a century ago, in 1916. Einstein posited that massive objects, like planets, stars, and especially black holes, don't just sit in this tapestry, they actually bend and warp it, much like a bowling ball placed on a trampoline. This bending is what we perceive as gravity, but Einstein's theory went further. He predicted that when these massive objects accelerate or collide with incredible violence, they don't just sit there, creating a static dimple. Instead, they send ripples, like waves on a pond, through this fabric of spacetime. These are gravitational waves, disturbances that propagate outwards at the speed of light, carrying with them information about the cataclysmic events that created them. It's a breathtaking idea that the very geometry of the universe itself can shudder and undulate. But even Einstein, the visionary who conceived them, harbored significant doubts about whether these minuscule ripples could ever be detected. He even, at one point, co-authored a flawed paper attempting to disprove their existence, a fascinating testament to the human struggle within even the greatest scientific minds. This wasn't just a theoretical curiosity. It was a whisper from the cosmos, a century-long detective story that began with a reluctant prediction. The quest to prove Einstein right, or at least to confirm the existence of these elusive waves, became a scientific odyssey spanning decades, filled with both brilliance and frustration. In the 1960s, a lone, passionate physicist named Joseph Weber pioneered the field, driven by an almost singular obsession. He built the first gravitational wave detectors, massive aluminum cylinders he called Weber bars. The idea was simple, yet audacious. A passing gravitational wave, he reasoned, should cause these bars to resonate, to vibrate ever so slightly. In 1969, Weber controversially claimed to have detected these waves. His initial announcements electrified the scientific community, but his results, despite intense scrutiny and numerous attempts by other labs, could never be replicated. Weber's claims eventually fell out of favor, leading to widespread skepticism and even ridicule. Yet, his unwavering belief and his pioneering, albeit ultimately unconfirmed experiments, galvanized the field. He laid the groundwork, inspiring a new generation of scientists to pursue the seemingly impossible, to build better, more sensitive instruments. He was the maverick, the lone voice in the wilderness, whose journey, though fraught with controversy, was a necessary step on the path to discovery. Then came the first indirect whisper, a subtle but undeniable clue that gravitational waves were real. In 1974, astronomers Russell Hulse and Joseph Taylor Joyce discovered a binary pulsar system, two neutron stars locked in a tight, dizzying cosmic dance, orbiting each other every 8 hours. Neutron stars are the incredibly dense remnants of collapsed massive stars, packing more mass than our Sun into a sphere only about the size of a city. This particular pair, known as the Hulse-Taylor binary pulsar, acted like a perfect cosmic clock. By precisely timing the pulses of radio waves emitted by one of the pulsars, scientists could measure their orbital decay with exquisite accuracy. And what they found was astonishing. The pair was spiraling inward, losing energy at precisely the rate predicted by Einstein's general theory of relativity if they were shedding that energy in the form of gravitational waves. This elegant, indirect proof earned Hulse and Taylor the Nobel Prize in Physics in 1993. It was a powerful confirmation that gravitational waves were not just theoretical constructs. They were out there, subtly shaping the universe, even if we couldn't yet directly hear them. It was like seeing the ripples on a pond and knowing a stone had been dropped, even if you hadn't seen the stone itself. But indirect evidence, however compelling, wasn't enough for the dedicated few who dreamed of a direct detection. They wanted to hear the stone drop. The challenge, however, was immense, almost ridiculously so. Gravitational waves cause incredibly tiny distortions in spacetime. We're talking about changes in distance thousands of times smaller than the nucleus of an atom. To put that into perspective, imagine trying to measure a change in the distance to the nearest star, Alpha Centauri, with the precision of a single human hair's width. That's the mind-boggling scale of the measurement required. It was a challenge that demanded an impossible machine, an instrument so sensitive it could detect the universe's most violent events while ignoring the gentle vibrations of the Earth itself. The concept for such a machine, using laser interferometry, began to take shape in the 1960s, with Rainer Weiss of MIT emerging as a key architect of the design. The idea was to split a single laser beam and send the two resulting beams down extremely long perpendicular arms. At the end of each arm, mirrors would reflect the beams back to their origin. If a gravitational wave passed through, it would momentarily stretch one arm while compressing the other, causing a tiny differential change in the path length of the two laser beams. When the beams recombined, this minuscule difference would create an interference pattern, a faint flicker that would be the signature of a passing gravitational wave. Simple in concept, impossibly complex in execution, this ambitious project eventually became the Laser Interferometer Gravitational Wave Observatory, or LIGO. It was a massive undertaking, becoming the largest project ever funded by the National Science Foundation (NSF). For decades, it faced significant technical hurdles, relentless skepticism, and political battles. It was a monumental gamble, a testament to human perseverance against overwhelming odds. The detectors themselves were engineering marvels. 2 observatories, thousands of miles apart, in Hanford, Washington, and Livingston, Louisiana, each housing 2 4-kilometer-long vacuum tubes. Inside these tubes, lasers bounced back and forth, attempting to achieve an unprecedented level of precision. They had to be isolated from every conceivable vibration. Seismic tremors, ocean waves, even the slightest breeze, or distant truck on a highway could drown out the faint whisper they were trying to hear. It was a battle against the Earth itself, a quest for a perfect, impossible silence in which the universe's whispers could finally be heard. Years passed. Upgrades were made. Scientists toiled. The world waited, largely unaware of the silent, century-long hunt unfolding. Then, in the early hours of September 14, 2015, just days after the newly upgraded advanced LIGO detectors began their first official engineering run, a signal arrived. It was faint, unmistakable, and utterly thrilling. It came simultaneously to both detectors, separated by a mere 7 milliseconds, precisely the travel time for light and gravitational waves between Livingston and Hanford. This near-simultaneous detection was crucial. It ruled out any local terrestrial noise and provided the first critical piece of evidence that this was a genuine cosmic event. What they had heard was the definitive chirp of GW150954, the first ever direct detection of a gravitational wave. It was the sound of 2 black holes, one approximately 36 times the mass of our Sun, the other 29 times, spiraling inward and eventually merging into a single monstrous black hole, 62 times the Sun's mass. In that final cataclysmic fraction of a second, an astonishing 3 solar masses of matter were converted directly into pure gravitational wave energy. To comprehend the sheer scale of this event, consider this. The peak power output during those final moments was approximately 50 times greater than the power output of all the visible stars in the observable universe combined. This titanic collision had occurred an unfathomable 1.3 billion light-years away from Earth, its ripples traveling across the vast expanse of the cosmos for an unimaginable length of time before finally, subtly, disturbing the detectors of LIGO. The chirp itself was a fleeting moment, lasting only about 0.2 seconds, sweeping up in frequency from 35 Hz to 250 Hz, as the black holes sped up their death spiral, like a cosmic siren, signaling the end of an era and the beginning of a new one. The initial reaction among the scientists was a mix of disbelief and exhilaration. Was it a prank? A blind injection test designed to keep them on their toes? Weeks of meticulous verification followed, rigorous checks and double checks of the data, ensuring that every possible terrestrial source of noise had been ruled out. But the signal remained, clear and undeniable. On February 11, 2016, the public announcement was made. The world learned that humanity had finally grown ears. The impact of that first detection was immediate and profound. It wasn't just a confirmation of Einstein's general theory of relativity, a century after its prediction. It was a revelation. It confirmed the existence of binary black hole systems, objects that had previously been theoretical curiosities. More importantly, it opened a brand new window onto the universe, launching the era of gravitational wave astronomy. We were no longer limited to observing the cosmos through the electromagnetic spectrum, light, radio waves, X-rays, gamma rays. Now, we could listen to the universe's most violent and hidden events, things that don't emit light, things that are shrouded in dust and gas. Gravitational waves cut through everything. They are not obstructed or altered by intervening matter, giving them the potential to reveal information From the very earliest moments of the universe, including the Big Bang itself, that is otherwise inaccessible, the simple chirp we heard was just the first note in a cosmic symphony. It was the aha moment, the moment humanity realized it had gained a new fundamental way to perceive reality. We had for so long been like ancient mariners navigating by starlight, unaware of the deep ocean currents beneath their ships. Now, we could feel those currents, listen to their powerful ancient flow. The universe, once a silent movie, had found its soundtrack, and the stories it was beginning to tell us through these echoes of space-time were more incredible than anything we could have imagined. We were no longer just seeing the universe. We were beginning to feel its pulse, to hear its heart. This was just the beginning of a whole new way to experience the cosmos, a journey into the unseen and the unheard, where the most extreme events in creation reveal themselves not in light, but in sound. And that, my friends, is a universe waiting to be heard. The simple chirp we heard was just the first note in a cosmic symphony. It was the aha moment, the moment humanity realized it had gained a new fundamental way to perceive reality. We had for so long been like ancient mariners navigating by starlight, unaware of the deep ocean currents beneath their ships. Now, we could feel those currents, listen to their powerful ancient flow. The universe, once a silent movie, had found its soundtrack, and the stories it was beginning to tell us through these echoes of space-time were more incredible than anything we could have imagined. We were no longer just seeing the universe. We were beginning to feel its pulse, to hear its heart. This was just the beginning of a whole new way to experience the cosmos, a journey into the unseen and the unheard, where the most extreme events in creation reveal themselves not in light, but in sound. And that, my friends, is a universe waiting to be heard. But to truly appreciate the incredible sound of colliding black holes, to understand how humanity finally grew ears to listen to the universe, we first have to grasp the instrument itself. Not a violin, not a drum, but something far more fundamental, far more profound: space-time. This isn't just the stage upon which the cosmic drama unfolds. It is the drama, the very fabric of existence, and it's the instrument played by the universe's most violent events. For most of human history, our understanding of the universe was built on what we could see. Our eyes, aided by ever more powerful telescopes, showed us galaxies swirling, stars blazing, nebulae unfurling like celestial masterpieces. We mapped the cosmos with light, interpreting every flicker and hue as a clue to its grand design. And for centuries, we understood gravity as a force, a mysterious, invisible pull that kept our feet on the ground and the planets in their orbits around the sun. Sir Isaac Newton famously described it as an instantaneous force, acting across vast distances without any medium. And for a long time, that explanation worked beautifully. It allowed us to predict the motions of celestial bodies with astonishing accuracy. But then, a young patent clerk named Albert Einstein stepped onto the stage of physics in the early 20th century, and he changed everything. He didn't just tweak our understanding of gravity. He completely reimagined it. Imagine for a moment that the universe isn't just empty space, a vast inert container where stars and planets float. Instead, picture it as a gigantic, flexible, four-dimensional fabric, a cosmic drum stretched taut across all of existence. This is space-time. It's not just space, and it's not just time. It's an inseparable fusion of the two. Now, imagine placing a bowling ball in the center of a trampoline. What happens? The trampoline sags. It curves. If you then roll a marble across the trampoline, it won't travel in a straight line. It'll curve inward towards the bowling ball, drawn by the distortion in the fabric. This, in essence, is Einstein's general theory of relativity, proposed in 1916. He told us that gravity isn't a force pulling us down. It's the curvature of this space-time fabric itself. Massive objects, like our sun, like Earth, like those colossal black holes, they don't pull on things. Instead, they warp the space-time around them. And what we perceive as gravity is simply objects following the curves that massive bodies have created in that fabric. This was an aha moment of monumental proportions. Gravity wasn't a force you could feel pulling you. It was the very shape of the universe guiding your path. It was elegant, beautiful, and profoundly counterintuitive. And it came with an extraordinary prediction. If massive objects curve space-time, and if those massive objects move or accelerate, then those curves should ripple, like a stone dropped into a pond, or a mallet striking a drum. These cosmic disturbances should send waves, gravitational waves, propagating outward through the fabric of space-time, carrying energy and information at the speed of light. Think of it like this. The universe's most massive and violent events are the mallets striking our cosmic drum. When two black holes, each 30 times the mass of our sun, begin their final furious death spiral, circling closer and closer before merging into one gargantuan entity, they aren't just creating a visual spectacle. They are pounding on the space-time drum. The energy released in that final fraction of a second, more powerful than all the stars in the observable universe combined, isn't just light. It's a colossal seismic event in the very fabric of reality. And the vibrations, the ripples from that impact, are gravitational waves. These waves are literally stretching and squeezing the universe as they pass through it. If a gravitational wave were to pass through you right now, it would momentarily make you infinitesimally taller and thinner, then shorter and wider, then taller and thinner again, before returning you to your normal shape. But don't worry, you wouldn't notice. That's because the effects are incredibly, mind-bogglingly tiny. Einstein's initial calculations suggested these ripples would be so faint, so minuscule, that detecting them would be an impossible feat. He even, at one point, grew skeptical himself, co-authoring a paper that incorrectly tried to argue gravitational waves didn't exist. It was a testament to the sheer audacity of his own theory and the seemingly insurmountable challenge he had presented to experimental physics. So, for decades, the idea of gravitational waves remained just that, a brilliant, elegant theoretical prediction, a whisper from the cosmos that seemed destined to remain unheard. It was Einstein's last, greatest whisper, echoing through the halls of theoretical physics, daring scientists to try and catch it. But the human spirit, especially the scientific spirit, is not easily deterred. The hunt was on, a century-long detective story to prove Einstein right. It began in earnest in the 1960s with a visionary, if ultimately controversial, physicist named Joseph Weber. Weber was a pioneer, a true maverick, who dared to dream of hearing the universe. He built the first gravitational wave detectors, massive aluminum cylinders, affectionately known as Weber bars. His idea was simple. If a gravitational wave passed through Earth, it would cause these large metal bars to resonate, to vibrate ever so slightly. He believed he had detected these elusive waves in 1969, reporting signals that no one else could replicate. Weber's claims were met with immense skepticism, but his work, though unverified, ignited the imagination of a generation of scientists. He laid the conceptual groundwork, proving that some people at least believed this whisper could be heard, and that it was worth dedicating one's life to the pursuit. He was, in a way, the first person to try and build an ear for the universe, even if it wasn't yet sensitive enough. The real breakthrough The first indirect proof that Einstein's whisper was indeed real came in 1974, not from a laboratory on Earth, but from the depths of space. Two astronomers, Russell Hulse and Joseph Taylor Jr., discovered a binary pulsar system, PSCR B1913+16. Imagine two incredibly dense, rapidly spinning neutron stars, the remnants of collapsed massive stars, locked in a tight, dizzying dance, orbiting each other every 8 hours. These pulsars emit beams of radio waves, like cosmic lighthouses, and as they spin, these beams sweep across Earth, allowing us to time their orbits with astonishing precision. What Hulse and Taylor observed was profound. The orbital period of these two neutron stars was gradually, steadily decreasing. They were spiraling closer and closer together, losing energy. And the rate at which they were losing energy perfectly matched what Einstein's general theory of relativity predicted if the system was emitting gravitational waves. It was like watching a perfectly synchronized clock, slowly winding down, with the missing energy exactly accounted for by the invisible ripples they were sending out into spacetime. This wasn't direct detection, but it was incredibly compelling evidence. A smoking gun that proved gravitational waves were not just theoretical constructs, but real phenomena shaping the cosmos. This groundbreaking discovery earned Hulse and Taylor the Nobel Prize in Physics in 1993, solidifying the scientific community's belief that gravitational waves were real, even if still undetectable by human instruments. This indirect proof fueled the dream, transforming it from a theoretical curiosity into an experimental imperative. If these waves were out there, then humanity had to find a way to hear them. But how? Joseph Weber's bars, for all their pioneering spirit, simply weren't sensitive enough. The challenge was immense. How do you measure a distortion in spacetime thousands of times smaller than the nucleus of an atom? It's like trying to detect a change in the distance to the nearest star with the precisions of a single human hair's width. This wasn't just hard science. It was borderline science fiction. The answer, it turned out, lay in light, specifically in the incredibly precise properties of laser light. The concept of using laser interferometry to detect gravitational waves began to take shape in the 1960s with a brilliant physicist named Rainer Weiss from MIT emerging as a key architect of the design that would eventually make the impossible possible. Weiss's idea was revolutionary in its simplicity, yet mind-boggling in its scale and precision. Imagine splitting a single beam of laser light into two, sending each beam down a perfectly perpendicular tunnel, bouncing them off mirrors at the end, and then recombining them. If the two beams travel exactly the same distance, they will recombine perfectly. But if a gravitational wave passes through, it would momentarily stretch one arm of the detector while squeezing the other, then vice versa. This tiny, infinitesimal change in distance, smaller than anything humanity had ever attempted to measure, would cause the recombined laser beams to be slightly out of phase, creating an interference pattern. This interference pattern would be the sound of the gravitational wave, the faint echo of the cosmic drum being struck. It was a brilliant concept, but the engineering challenges were beyond daunting. You would need tunnels kilometers long, mirrors so perfectly polished they were virtually flawless, and vacuums so profound that almost all air molecules were removed, preventing any tiny particle from scattering the laser light. You would need seismic isolation systems so sophisticated they could filter out every tremor from the Earth itself, ocean waves, distant earthquakes, even a truck rumbling down a road miles away. The Earth, in its constant motion and subtle vibrations, was a noisy place, and scientists needed to find a way to create an island of perfect stillness, a sanctuary of silence, in which to listen for the universe's most elusive whispers. This wasn't a job for one brilliant mind, or even a small team. It would require a massive, sustained global collaboration, pooling the resources, intellect, and sheer perseverance of thousands of scientists and engineers from around the world. It would become the largest and most ambitious project ever funded by the National Science Foundation in the United States. This was the genesis of the Laser Interferometer Gravitational Wave Observatory, or LIGO. The story of LIGO is a testament to human ingenuity, patience, and unwavering belief in the power of curiosity. For decades, it was a dream, a theoretical possibility, a massive construction project plagued by technical hurdles and the skepticism of those who doubted such a faint signal could ever be detected. Scientists like Rainer Weiss, along with theoretical physicist Kip Thorne, who meticulously calculated the precise waveforms that different cosmic events, like colliding black holes, would produce, dedicated their entire careers to this quest. Later, Barry Barish would join, transforming the struggling project with his leadership and vision, scaling it into the successful global collaboration that would eventually deliver the goods. These were the titans, the visionaries who picked up Einstein's whisper and dared to turn it into a roar. They were not just building a scientific instrument, they were building an ear for humanity, an extension of our senses that would finally allow us to perceive the universe in a way we had only dreamed of. For a century, Einstein's prediction had hung in the air, a tantalizing mystery. The idea that gravity wasn't just a force, but the very curvature of spacetime, and that this curvature could ripple at the speed of light, carrying with it the raw power of the universe's most catastrophic events, was a profound shift in our understanding of reality. And now, thanks to the tireless efforts of these scientific pioneers, the stage was being set for humanity to finally listen in. We were, in essence, preparing to hear the universe play its cosmic drum. And the first notes, when they finally came, would forever change how we understood our place within its grand, symphonic, and now audible design. The silence was about to be broken. The silence was about to be broken, but not without a fight. For a century, humanity had lived under a vast cosmic hush, our eyes our only windows to the universe. We saw the fireworks of supernovae, the majestic spirals of galaxies, the birth pangs of stars and nebulae. But what if there was a whole other dimension to the cosmos, a symphony playing out that we were simply deaf to? What if the grandest, most violent events in the universe weren't just seen, but felt as ripples in the very fabric of existence? This was the audacious idea Albert Einstein tossed into the ocean of science in 1916. Imagine for a moment space-time not as an empty, unchanging stage, but as a vast, flexible sheet. A bowling ball placed on it would create a dip, an indentation. That, in essence, is what gravity is, the curvature of this sheet caused by mass. Now, imagine two of those bowling balls, or say, two colossal black holes, spiraling around each other, dancing a death waltz at unimaginable speeds. Their violent motion would send tremors, ripples, through that sheet of space-time, expanding outwards at the speed of light. These, he proposed, were gravitational waves. It was a profound, almost poetic concept, a cornerstone of his general theory of relativity. But even Einstein, the man who dreamed up this cosmic ballet, grew skeptical. The effects of these waves, he reasoned, would be so infinitesimally small by the time they reached us that detecting them would be an impossible feat. He even co-authored a paper at one point, attempting to disprove their existence entirely, though that paper later turned out to be flawed. Think about that for a second. The genius himself, the one who sent this profound message in a bottle across the vast ocean of theoretical physics, lost hope that anyone would ever find it. That doubt, that human fallibility, from even the greatest minds, only deepens the triumph of those who kept searching. His message in a bottle was adrift, a theoretical whisper lost in the cosmic static, waiting for someone to build a net sophisticated enough to catch it. And so began the 100-year hunt, a scientific odyssey filled with brilliant minds, controversial detours, and the unwavering belief that the universe had more to tell us if only we could learn to listen. The first brave soul to cast a net, however rudimentary, was an American physicist named Joseph Weber. This was in the 1960s, decades after Einstein's initial prediction. Weber was a maverick, a pioneer in the truest sense, and he dedicated himself to the impossible. He envisioned giant, solid aluminum cylinders, what became known as Weber bars, suspended in a vacuum, carefully isolated from terrestrial vibrations. His idea was elegant in its simplicity. If a gravitational wave passed through Earth, it would cause these massive bars to subtly expand and contract, resonating ever so slightly. He believed if he could measure that microscopic jiggle, he would have caught Einstein's elusive ripple. Weber was a man ahead of his time, driven by an almost singular obsession. In 1969, he controversially announced he had detected gravitational waves. The scientific world buzzed with a mix of excitement and skepticism. Here was a claim that, if true, would reshape our understanding of the universe. Other labs around the world scrambled to replicate his results, building their own Weber bars. But try as they might, no one could consistently confirm what Weber claimed to see. His signals were, to put it mildly, ambiguous, often appearing to be buried in the noise of everyday existence. Weber's claims were ultimately unsubstantiated, and his reputation suffered. It was a painful public setback. But here's the thing about true scientific endeavor. Even perceived failures can sow the seeds for future triumphs. Weber, despite his controversies, lit a fire. He showed the world that this wasn't just theoretical musing. It was a physical phenomenon worth chasing, a prize worth fighting for. He demonstrated the immense difficulty, the extraordinary precision required. And in doing so, he galvanized a new generation of scientists, inspiring them to build better, far more sensitive nets. His failure was, in a profound way, a crucial step forward, a testament to the power of human curiosity, even when it sometimes leads down a blind alley. The next major breakthrough in this long hunt wasn't about hearing the waves directly, but about seeing their effect. It was another kind of message in a bottle, a beautiful piece of indirect evidence that arrived in 1974, discovered by two astronomers, Russell Hulse and Joseph Taylor Jr. They were studying a binary pulsar system, PSR B1913T+16, located about 21,000 light-years away. Now, a pulsar, if you're not familiar, is a rapidly spinning neutron star, the super-dense remnant of a collapsed giant star that emits beams of electromagnetic radiation like a cosmic lighthouse. As it spins, these beams sweep across Earth, and we detect them as incredibly precise, rhythmic pulses. Hulse and Taylor found something extraordinary. Two of these neutron stars, locked in a tight, dizzying orbit around each other. What made this system so crucial was the almost clockwork precision of their pulses. By meticulously timing these pulses over years, they could track the orbital decay of the binary system with breathtaking accuracy. And what they discovered was a perfect match for Einstein's predictions. The two neutron stars were slowly, almost imperceptibly, spiraling closer together. They were losing energy, and the only known mechanism that could account for this energy loss was the emission of gravitational waves. It was the first undeniable, albeit indirect, proof proof that Einstein's ripples in spacetime were real. This wasn't catching the message in the bottle itself, but finding the empty bottle lying on the shore, still damp with salt water, with a note inside saying, "A message was here." The implications were staggering. For this elegant confirmation of general relativity, Hulse and Taylor were awarded the Nobel Prize in Physics in 1993, a testament to the power of observation and the subtle ways the universe reveals its deepest secrets. Their discovery was a profound validation for everyone who believed that Einstein's dream was not only possible, but already subtly shaping the cosmos. The indirect evidence from the Hulse-Taylor pulsar, while revolutionary, only fueled the desire for direct detection. We wanted to hear the universe, not just infer its whispers. And by this time, the scientific community had begun to shift its focus from Weber's resonant bars to a far more ambitious and sensitive technology: laser interferometry. This was where another visionary, Rainer Weiss, an MIT physicist, played a pivotal role. In the late 1960s and early 70s, independently and in collaboration with others, Weiss laid out the theoretical framework and conceptual design for a gravitational wave detector that would use lasers to measure minuscule changes in distance. Imagine two long, perfectly straight tunnels forming an L shape, each stretching for kilometers. At the corner where they meet, you split a single laser beam. One beam shoots down one arm, bounces off a mirror at the end, and returns. The other beam does the same down the perpendicular arm. When they return, these two beams are recombined. If nothing has disturbed space-time, the light waves will be perfectly in sync, creating a specific interference pattern. But if a gravitational wave passes through, it will momentarily stretch space-time in one direction, while compressing it in the perpendicular direction. This minuscule distortion, far smaller than an atom, would cause one arm of the detector to get infinitesimally longer, and the other infinitesimally shorter. Even for a fleeting moment, this difference in length would throw the laser beams out of sync, altering their interference pattern. That, in essence, would be the signal, the universe's cosmic drumbeat, manifesting as a flicker in light. The scale of the challenge was almost beyond comprehension. We're talking about detecting a change in distance equivalent to 1,000th the diameter of a proton. Think about that. It's like trying to measure a change in the distance to the nearest star with the precision of a single human hair's width. This wasn't just building a detector. It was building an impossible machine, a testament to humanity's relentless pursuit of the limits of measurement. The vision of laser interferometry was technically daunting, requiring ultra-high vacuums to prevent air molecules from disturbing the laser beams. Seismic isolation systems so precise they could dampen the vibrations of distant ocean waves or even a truck rumbling miles away, and lasers of unprecedented purity and stability. This wasn't a project for a lone scientist in a garage. This was a grand collaborative endeavor that would require decades of sustained effort, billions of dollars, and the dedication of thousands of the brightest minds across the globe. The idea for what would become the Laser Interferometer, Gravitational Wave Observatory, or LIGO, began to take shape. It would be a monumental undertaking, facing not only immense technical hurdles, but also significant skepticism from within the scientific community and from funding bodies. Could such an impossibly sensitive instrument ever actually work? Would the signal, if it existed, be forever lost in the cacophony of terrestrial noise? The path from theory to proof, from Einstein's initial whisper to the eventual roar, was indeed a long, arduous struggle. It was a journey paved with the ghosts of failed attempts, brilliant side quests that yielded indirect proof, and the unwavering belief that the universe was playing a symphony we were destined to hear. The message in a bottle had been cast, and generations of scientists standing on the shoulders of giants like Einstein, and learning from the bold, if unconfirmed, efforts of pioneers like Weber, we're now building the most complex sensitive nets imaginable. They were driven by an insatiable curiosity, a profound sense of wonder, and the quiet conviction that one day the silence would indeed be broken, and the universe would finally reveal its deepest, most violent secrets in a sound we could all hear. The stage was set, the instruments were being tuned, and the 100-year hunt was drawing to its astonishing close. The path from theory to proof, from Einstein's initial whisper to the eventual roar, was indeed a long, arduous struggle. It was a journey paved with the ghosts of failed attempts, brilliant side quests that yielded indirect proof, and the unwavering belief that the universe was playing a symphony we were destined to hear. The message in a bottle had been cast, and generations of scientists, standing on the shoulders of giants like Einstein, and learning from the bold, if unconfirmed, efforts of pioneers like Weber, were now building the most complex, sensitive nets imaginable. They were driven by an insatiable curiosity, a profound sense of wonder, and the quiet conviction that one day the silence would indeed be broken, and the universe would finally reveal its deepest, most violent secrets in a sound we could all hear. The stage was set, the instruments were being tuned, and the 100-year hunt was drawing to its astonishing close. Imagine for a moment that you are trying to hear the faintest whisper from across a bustling city street. Now imagine that whisper isn't even a sound carried by air, but a ripple in the very pavement beneath your feet, a distortion so infinitesimally small, it's like trying to feel the gravitational pull of a single grain of sand from a mile away. This is the scale of the challenge that faced scientists intent on listening to the universe's most violent events. To hear the cosmos speak, they had to build the quietest place on Earth. Not quiet in terms of sound, no, but quiet in terms of vibration, of disturbance, of anything that could mimic the universe's subtle song. They had to construct one of the most sensitive and silent machines in human history. The Laser Interferometer, Gravitational Wave Observatory, or LIGO. LIGO isn't just a telescope, it's a cosmic ear, an engineering marvel born of decades of relentless pursuit, a testament to human ingenuity against seemingly insurmountable odds. And its core mission is deceptively simple: to measure an impossible distance. Think of it like this: LIGO is a ruler, but not just any ruler. It's a ruler for space-time itself. This isn't some abstract metaphor. It's the beating heart of how it works. Picture two enormous L-shaped facilities, one nestled in the desert plains of Hanford, Washington, and the other tucked away in the pine forests of Livingston, Louisiana. Each facility boasts two arms, 4 kilometers, about 2.5 miles long, stretching out into the landscape like colossal, perfectly straight antennae. These aren't just hollow tubes. They are the most pristine vacuum chambers ever created on Earth, evacuated to a pressure so low, it's 1 trillion times less than the air you breathe. Inside these arms, precisely tuned laser beams shoot back and forth, bouncing off mirrors of unimaginable perfection. These lasers are your measuring tape, and the mirrors are your markers. Here's the genius of it. The two laser beams travel down each of the 4-kilometer arms, hit mirrors at the end, and bounce back to meet at a central detector. In a perfectly stable universe, if both arms are exactly the same length, the laser beams will arrive back at the detector precisely out of phase, canceling each other out, resulting in darkness. It's a delicate dance of light, an exquisite balance. But if a gravitational wave passes through Earth, it momentarily stretches space-time in one direction and compresses it in another, ever so slightly. This means one of LIGO's arms will become infinitesimally shorter, while the other becomes infinitesimally longer. Even for the briefest, most fleeting moment, the arms are no longer perfectly equal. And that, my friends, is where the magic happens. Even that minuscule momentary difference in arm length causes the laser beams to arrive back at the detector slightly out of sync. Instead of canceling each other out completely, a flicker of light appears. It's an almost imperceptible signal, a whisper in the dark, but it is the universe speaking. This flicker, this tiny change in the interference pattern of the light, is what LIGO is designed to detect. It's how we hear the universe. But let's be clear about the scale of minuscule. We are talking about a change in distance equivalent to 1,000th the diameter of a proton. Think about that for a second. A proton itself is already unimaginably small, a fundamental building block of every atom in your body. Now divide its width by 1,000. That's the distortion in spacetime. LIGO is sensitive enough to measure across its 4-kilometer arms. To put it another way, it's like measuring the distance to the nearest star, Proxima Centauri, with the precision of a single human hair's width. It's a level of precision that boggles the mind, an almost absurd ambition that defines the very essence of human scientific endeavor. This brings us to the aha moment, the profound realization that the most significant hurdle wasn't just building a machine sensitive enough to detect such an impossibly faint signal, but silencing the cacophony of our own world. The primary challenge wasn't listening for the universe's whisper, but quieting the relentless noise of Earth itself. From the moment the concept of using laser interferometry to detect gravitational waves was proposed in the 1960s, with Rainer Weiss of MIT being a key architect of the design, the scientists understood that the enemy wasn't just the weakness of the signal, but the strength of the noise. First, there are the seismic tremors. The ground beneath our feet is never truly still. Distant earthquakes, microseisms caused by ocean waves crashing on distant shores, even the gentle sway of the wind against trees, all of these create tiny vibrations that travel through the Earth's crust. If these vibrations reached LIGO's delicate mirrors, they would utterly swamp any gravitational wave signal. To combat this, LIGO's mirrors aren't simply bolted to the ground. Oh no. They are suspended like priceless jewels in a series of exquisitely engineered, multi-stage pendulums. Imagine a system of nested platforms, each one suspended by wires, forming a complex, almost artistic isolation system. Each stage filters out more of the terrestrial noise, like a series of increasingly fine sieves, ensuring that only the most isolated, pristine environment remains for the mirrors. These active seismic isolation systems are masterpieces of engineering, constantly sensing ground motion and counteracting it with minute, precise adjustments. Then there's the noise from human activity. Trucks rumbling down a highway miles away, trains passing, even the faint footsteps of a scientist walking through the building. Every single one of these seemingly innocuous activities generates vibrations that, while imperceptible to us, are titanic compared to the ripples in spacetime. LIGO is trying to detect. The entire LIGO facility, particularly around the detector areas, is designed to be a sanctuary of stillness, a place where human presence is minimized, and any necessary movements are carefully controlled to prevent unwanted disturbances. It's a constant battle against the very vibrations of life itself. And what about the air? Even the slightest air currents, the movement of a single air molecule, could perturb the laser beams, causing false signals. This is why those 4-kilometer arms are not just empty spaces. They are ultra-high vacuum chambers, the largest and purest vacuums ever created. Massive pumps work tirelessly, around the clock, to suck out virtually every single air molecule. The level of vacuum achieved is so extreme that if you were to open a tiny pinhole in one of the arms, it would take centuries for enough air to enter to bring the pressure up to atmospheric levels. This monumental effort ensures that the laser beams have an unimpeded, perfectly stable path, free from the interference of even the most minute airborne particles. Beyond mechanical and environmental noise, there's also the fundamental noise inherent in the detection process itself. The lasers, for instance, must be incredibly stable and powerful, yet also perfectly pure. Any fluctuations in their intensity or frequency could be misinterpreted as a signal. Scientists had to develop some of the most advanced laser technology on Earth, creating beams of light that are not only incredibly powerful, but also remarkably quiet, free from the quantum jitters that could otherwise obscure the faint gravitational wave signal. And the mirrors themselves? They are not just ordinary mirrors. They are polished to an atomic scale of smoothness, coated with multiple layers of ultra-precise materials to ensure maximum reflectivity and minimum light absorption. Even the thermal vibrations of the atoms within the mirrors themselves could be a source of noise, so the mirrors are designed to be as thermally stable as possible. The collective effort to achieve this unparalleled level of silence and sensitivity is staggering. It's a testament to the visionaries like Rainer Weiss, whose early conceptualizations laid the groundwork for this monumental undertaking, and to the thousands of scientists and engineers from over 120 institutions across 19 countries who formed the LIGO Scientific Collaboration, LIC. This wasn't a project that a single genius could complete in isolation. It required a global army of minds, each contributing to solve a piece of this colossal puzzle. It became the largest project ever funded by the National Science Foundation, NSF, a testament to the belief that this seemingly impossible dream was worth every ounce of effort and every dollar invested. But even with the most advanced seismic isolation, the purest vacuums, and the most stable lasers, how could you be sure that a tiny flicker of light wasn't just some local disturbance, a stray truck, or a distant tremor? This is where the geographic separation of the two LIGO detectors in Washington and Louisiana becomes absolutely crucial. A true gravitational wave, traveling at the speed of light, would pass through both detectors, arriving at one slightly before the other due to the curvature of the Earth. A local vibration, a truck or an earthquake, would only affect one site. It's like having two ears, miles apart, to ensure you're not just hearing an echo of your own world, and then to truly confirm a cosmic event and pinpoint its origin in the vastness of space. A third ear was needed. The addition of the Virgo detector in Italy, and later Kagra in Japan, expanded this network into a global observatory. With 3 or more detectors spread across the planet, scientists could triangulate the source of a gravitational wave with much greater accuracy, distinguishing between a true cosmic signal and local noise, providing critical verification and allowing telescopes to then turn their gaze to the exact patch of sky where a violent event had just unfolded. So, to return to our initial thought experiment, imagine trying to hear that whisper from across the city. LIGO didn't just try to listen harder. It built an entirely new silent city around its ear. It created a bubble of unparalleled stillness, a sanctuary of science where the relentless clamor of Earth could be muted, allowing the faintest, most profound whispers from the far reaches of the universe to finally be heard. The universe was indeed playing its symphony, a symphony of collapsing stars and colliding black holes. It was a sound that had been traveling for billions of years, a profound message in a bottle, waiting for us to silence ourselves enough to receive it. And after decades of relentless effort, of battling against the very fabric of our own noisy planet, Humanity was finally ready to listen. The stage was set. The cosmic ruler was honed to an impossible precision, and the universe was about to speak for the very first time. That sound? It's the universe speaking loud and clear. It's the collision of two black holes, each around 30 times the mass of our sun. It happened 1.3 billion years ago, long before anything remotely resembling human life graced our pale blue dot. And the energy released in that final fraction of a second, the very last gasp of their spiraling death dance, was more powerful than all the stars in the observable universe combined. We didn't see it. We heard it. This is the story of that sound, the chirp heard round the world, and how humanity finally grew ears to listen to the cosmos. For over a century, since Albert Einstein first wove the intricate tapestry of spacetime into his general theory of relativity in 1916, gravitational waves were theoretical ghosts, whispers on the cosmic wind that seemed forever beyond our grasp. He predicted them, these ripples in the very fabric of space and time. But even he, the brilliant architect of modern physics, doubted we'd ever be able to detect them. Their effects, he reasoned, would be too infinitesimally small, too subtle to register against the roaring symphony of our own planet. Think of it like this. For all of human history, astronomy was a visual art. We were like a species born with only eyes, gazing up at the night sky, charting the stars, marveling at nebulae, and tracing the paths of planets. Every discovery, every new insight came through light, whether it was visible light, radio waves, X-rays, or gamma rays. Our universe was a silent movie, breathtakingly beautiful, but utterly mute. We saw the fireworks, the cosmic ballets, the explosions, but we never heard the boom. The idea that space itself could vibrate, could carry sound like waves from the most cataclysmic events in the universe, was mind-bending. The journey to hear those whispers was a long, often frustrating, and frequently doubted quest. In the 1960s, a visionary physicist named Joseph Weber pioneered the field, building large aluminum cylinders called Weber bars, designed to resonate ever so slightly when a gravitational wave passed through them. He claimed to have detected them, sending ripples of excitement through the scientific community. But tragically, his results could never be replicated by others. His ambition, though ultimately unconfirmed, lit a crucial spark, inspiring a new generation of scientists to pursue this seemingly impossible dream. It was a necessary, if controversial, first step in what would become a 100-year hunt for the universe's most profound echoes. Then came the indirect evidence, a crucial harbinger of what was to come. In 1974, Russell Hulse and Joseph Taylor Jr. discovered a binary pulsar system, two incredibly dense neutron stars orbiting each other. Over years of meticulous observation, they noticed something extraordinary. The pulsar's orbit was slowly, precisely decaying. They were losing energy, spiraling inwards at a rate that perfectly matched Einstein's predictions for systems emitting gravitational waves. It was like seeing footprints in the snow and knowing with absolute certainty that someone had walked there, even if you hadn't seen them yourself. This indirect proof earned Hulse and Taylor the Nobel Prize in Physics in 1993, validating the theory and fueling the fire for direct detection. But indirect evidence, no matter how compelling, isn't the same as a direct observation. We needed to hear the universe directly. This monumental task fell to a project called LIGO, the Laser Interferometer Gravitational Wave Observatory. It was an audacious undertaking, a scientific endeavor of unparalleled scale and precision, conceived and championed by visionaries like Rainer Weiss, Kip Thorne, and later, managed by Barry Barish. Weiss, a brilliant experimentalist from MIT, was instrumental in developing the laser interferometer concept itself, realizing that light could be used to measure these infinitesimal ripples. Kip Thorne, a theoretical physicist from Caltech, provided the crucial theoretical framework, predicting the exact waveforms that scientists should look for from various cosmic events. And Barry Barish, with his exceptional leadership, transformed the struggling project into the successful global collaboration it is today. They were the architects of this new sense for humanity, building the ears we so desperately needed. LIGO, at its heart, is a pair of colossal L-shaped instruments, one nestled in Livingston, Louisiana, and the other in Hanford, Washington. Each arm of the L stretches 4 kilometers, forming the longest rulers ever built to measure the universe. Inside these arms, powerful lasers are split, sent down each tunnel, bounced off mirrors at the ends, and then recombined. If a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction, causing one arm to momentarily lengthen and the other to shorten by an infinitesimal amount. This tiny distortion creates a minuscule difference in the paths of the laser light, which, when recombined, creates an interference pattern that LIGO can detect. When we say infinitesimal, we mean it. LIGO had to be sensitive enough to detect a change in distance equivalent to 1,000th the diameter of a proton. Imagine trying to measure a change in the distance to the nearest star, Alpha Centauri, with the precision of a single human hair's width. That's the mind-boggling scale of what LIGO was designed to achieve. It was a battle against every conceivable source of noise: seismic tremors from distant earthquakes, the relentless pounding of ocean waves, the subtle vibrations from nearby traffic. Even the rustling of leaves or the footsteps of a mouse could, theoretically, drown out a cosmic whisper. The engineering challenges were immense, requiring ultra-high vacuums to prevent air molecules from disturbing the lasers, and sophisticated seismic isolation systems to shield the detectors from Earth's constant rumblings. It was truly a ghost in the machine narrative, a quest to find the perfect silence within our noisy world. For decades, the detectors hummed and whirred, constantly being upgraded, refined, and perfected. The International LIGO Scientific Collaboration, LSC, a massive global effort comprising over 1,400 scientists from more than 120 institutions across 19 countries, poured their lives into this dream. They built and tested. They analyzed data that revealed nothing but terrestrial noise, and they persevered through skepticism and setbacks. The world watched, waited, and wondered if Einstein's ghost would ever truly materialize. Then came September 14th of 2015. It was 5:51 a.m. Eastern Daylight Time, 0951 UTC. The advanced LIGO detectors, fresh from a major upgrade that had dramatically increased their sensitivity, had only just begun their first official engineering run, a trial period to fine-tune the instruments before full scientific observations commenced. Most scientists involved hadn't expected to see anything significant for months, perhaps even years. The universe, it seemed, had other plans at both the Livingston, Louisiana, and Hanford, Washington observatories. A signal registered almost simultaneously. The Livingston detector picked it up first, a mere 7 milliseconds before Hanford, precisely the time difference expected for a wave traveling at the speed of light across the Earth from a source in the southern hemisphere. The signal itself was extraordinary. It was a chirp, a distinct rising tone, sweeping upwards in frequency and amplitude over a mere 0.2 seconds. It started around 35 hertz, a low rumble, and rapidly ascended to about 250 hertz, a higher-pitched squeak, before abruptly cutting off. This was not just noise. This was a perfectly formed textbook example of a gravitational wave, exactly matching the complex waveforms predicted by Kip Thorne and his theoretical colleagues for the inspiral and merger of two massive objects. The first reaction among the scientists, despite decades of anticipation, was not celebration, but sheer disbelief. It was too perfect, too strong, too soon. This was the aha moment, a signal so immaculate, it felt like a prank. Had someone, perhaps as a test, injected a blind injection, a fake signal into the system? This was a common practice during the testing phases, where only a handful of scientists knew when such injections occurred, to ensure the collaboration's analytical tools and human vigilance were up to snuff. But this wasn't one of those times. No blind injections had been scheduled for this engineering run. Many of us didn't believe it. Rainer Weiss would later quip, reflecting on those tense hours and days. It took us 2 months to convince ourselves that we had detected a gravitational wave. The data designated GW150914, gravitational wave, September 14, 2015, triggered an immediate clandestine lockdown within the LIGO scientific collaboration. For months, a core team of scientists worked in absolute secrecy, scrutinizing every single pixel of data, every tremor, every potential source of terrestrial noise. They tried to prove it was a fluke, an artifact, a false alarm. They threw every statistical test, every computational model, and every ounce of their collective skepticism at it. They checked and rechecked the calibration of their instruments, the integrity of their vacuum systems, the purity of their lasers. They looked for any possible earthly explanation, any hidden glitch, any stray squirrel or passing truck that could have mimicked such a profound signal. Imagine the pressure. After half a century of relentless pursuit, after billions of dollars and countless hours of dedicated research by thousands of people, the universe had finally spoken. But was it real? The responsibility to be absolutely certain was immense. The scientific community had been burned before by unconfirmed claims, most notably by Joseph Weber. This time, there could be no doubt. What they found, after months of rigorous, painstaking verification, was not a fluke. It was real. The signal, they concluded, was indeed the gravitational echo of two black holes spiraling inwards, accelerating to nearly half the speed of light, and then violently merging into a single, more massive black hole. The initial black holes were estimated to be about 36 and 29 times the mass of our Sun, respectively. In that final fraction of a second, as they coalesced, a staggering 3 solar masses of energy were converted directly into gravitational waves, radiating outwards across the cosmos. This burst of gravitational energy, for that fleeting moment, was 50 times more powerful than all the light emitted by all the stars in the observable universe combined. The resulting merged black hole had a mass of approximately 62 solar masses. The missing 3 solar masses, that was the pure energy that warped spacetime itself, sending those ripples across 1.3 billion light-years to finally tickle LIGO's detectors on Earth. This was it, the first direct observation of gravitational waves, the first time humanity had ever heard the universe speak in its most fundamental language. It wasn't just a confirmation of Einstein's century-old prediction. It was the first photograph of a ghost. For a century, binary black holes were theoretical constructs, shadowy figures lurking in the equations of general relativity. Now, with GW150914, we had not only proven they existed, but we had witnessed their violent, awe-inspiring end, not with light, but with the gravitational echo they left behind. We had glimpsed the invisible, not with our eyes, but with a newly acquired sense. The public announcement came on February 11, 2016, months after the initial detection. The world reacted with a mix of awe, wonder, and a profound sense of triumph. Newspapers, scientific journals, and news outlets around the globe heralded the discovery as one of the most significant scientific achievements of the century. It immediately opened an unprecedented new window onto the cosmos, launching what scientists called the era of gravitational wave astronomy. This wasn't just another scientific discovery. It was a sensory revolution. For millennia, our understanding of the universe was limited by what we could see. Now, we had grown ears. We could listen to the universe's most violent events, not as distant points of light, but as visceral auditory experiences. The chirp of gravitational was more than just a sound. It was the universe's first spoken word to humanity, a profound message in a bottle that had traveled for eons, waiting for us to silence ourselves enough to receive it. And it was just the beginning. The stage was now truly set, and the cosmos, we realized, had an entire symphony waiting to be heard, and a profound sense of triumph. Newspapers, scientific journals, and news outlets around the globe heralded the discovery as one of the most significant scientific achievements of the century. It immediately opened an unprecedented new window onto the cosmos, launching what scientists called the era of gravitational wave astronomy. This wasn't just another scientific discovery. It was a sensory revolution. For millennia, our understanding of the universe was limited by what we could see. Now, we had grown ears. We could listen to the universe's most violent events, not as distant points of light, but as visceral auditory experiences. The chirp of GW1FIMS0914 was more than just a sound. It was the universe's first spoken word to humanity, a profound message in a bottle that had traveled for eons, waiting for us to silence ourselves enough to receive it. And it was just the beginning. The stage was now truly set, and the cosmos, we realized, had an entire symphony waiting to be heard. But what if the universe wasn't content with just a single spoken word? What if it had an entire complex story to tell us? A narrative woven through multiple senses, waiting for us to develop the capacity to receive it all. That's the extraordinary leap we took just 2 years after that initial breathtaking chirp. It was a moment that didn't just expand our hearing. It gifted us a new way of understanding, a cosmic Rosetta Stone that would finally unlock one of the universe's most ancient and glittering secrets. Imagine, if you will, the universe as a vast, dark concert hall. For eons, we sat in the audience, only able to see the stage lights, the dazzling visual spectacle of stars and galaxies. Then, with LIGO, we suddenly heard the first powerful bass note, the deep rumble of colliding black holes. It was overwhelming, a revelation. But then, on August 17, 2017, the entire orchestra swelled. The violins joined in, the trumpets blared, and the percussion exploded. We didn't just hear the universe that day. We began to truly listen to its full, multi-sensory symphony. This was the day we detected GW170817. And it wasn't just another chirp. Oh no. This was different. GW1FIV0914. That initial symphony of black holes was a colossal event, yes, but it was also, in a way, a silent one. At least in terms of traditional light. Black holes are, well, black. They don't emit light, so while LIGO heard their titanic embrace, the universe's telescopes, scanning the same distant galaxies, saw nothing out of the ordinary. It was like hearing a thunderclap, without seeing the lightning flash. Profound, yes, but incomplete. GW170817 was the cosmic lightning strike we had been waiting for. It was the sound of 2 neutron stars, locked in a death spiral, each one an unfathomably dense, city-sized remnant of a star that had exploded long ago. These aren't your average stars. These are the universe's ultimate heavyweights, packing more mass than our entire sun into a sphere no larger than a bustling metropolitan city. Imagine that. A spoon of neutron star material would weigh billions of tons here on Earth. As these two stellar titans spiraled inward, their orbits decaying, they began to accelerate, whipping around each other faster and faster. The gravitational waves they emitted grew stronger, their frequency rising, like the frantic crescendo of a cosmic alarm clock. For about 100 seconds, LIGO and its sister detector, Virgo, in Italy, registered this rising chirp, a signal that painted a picture of an impending, utterly catastrophic collision. This was the moment. This was the event that would forever change our understanding of the cosmos, ushering in the groundbreaking era of multi-messenger astronomy. Because just 1 milliseconds after the gravitational waves from GW17081 slammed into Earth, a different kind of signal arrived. A flash of gamma rays blazing across the universe, detected by NASA's Fermi Gamma Ray Space Telescope. It was the universe speaking to us, not just with its gravitational voice, but with its fiery electromagnetic tongue. And for the first time, we had two different languages, gravity and light, describing the very same event, allowing us to unlock secrets we never could with one alone. This was our Rosetta Stone of the cosmos. Think about the sheer mind-bending implications of this. For all of human history, astronomy has been a visual science. We've peered through telescopes, collected light, and built our cosmic narrative brick by painstaking brick, based on what our eyes or our instruments could see. But light, as powerful as it is, has limitations. It can be absorbed, scattered, or blocked by the vast clouds of dust and gas that permeate the universe. It's like trying to understand a complex story by only reading selected pages or listening to a symphony through a thick wall. Gravitational waves, however, are utterly oblivious to these cosmic obstacles. They ripple through everything unimpeded. They are the ultimate cosmic messengers, carrying information from places and events that light can never reach. So, when GW17081 hit, we were suddenly given two perfectly synchronized accounts of the same cataclysm. The gravitational waves told us about the dance of the neutron stars, their masses, their final moments before impact. The gamma rays, and then a cascade of other electromagnetic signals, told us about the explosive aftermath, the fiery debris, the visible consequences. The synergy was astonishing. The gravitational wave data allowed scientists to pinpoint the event's location in the sky with unprecedented accuracy, narrowing it down to a patch of sky containing approximately 50 galaxies. This was a crucial piece of the puzzle, because it allowed traditional telescopes, those magnificent eyes we'd always relied on, to swivel and stare directly at the source. And stare they did. Over 70 observatories around the world, both on Earth and in space, immediately turned their gaze toward the galaxy NGC 4993, located about 140 million light-years away in the constellation Hydra. They weren't just looking, they were hunting. What they found was nothing short of miraculous. Where before, there was only the faint, distant glow of a galaxy, now there was a new, brilliant point of light, fading rapidly. This wasn't a supernova, the familiar death explosion of a massive star. This was something new, something more exotic, something entirely more profound. This was a kilonova. The name itself, kilonova, hints at its immense power, roughly 1,000 times brighter than a classical nova, though still less luminous than a supernova. But it's not the brightness that makes a kilonova so utterly captivating. It's what's happening inside that explosion. When those two neutron stars finally collided, they didn't just smash together and disappear. Oh no. The impact was so violent so unbelievably energetic that it created conditions unlike anything else in the cosmos, conditions that allowed for an alchemical process of truly cosmic proportions. Imagine the forces at play. Two objects, each with the gravitational pull of a sun, spinning at incredible speeds, finally embracing in a cataclysmic, universe-shaking crunch. The material from these neutron stars, already compressed to unimaginable densities, was subjected to pressures and temperatures that defy earthly comprehension. In that fleeting, furious moment of collision, as the neutron stars merged, and then, for a brief, incandescent instant, likely formed a hypermassive, rapidly spinning neutron star before collapsing into a black hole, a torrent of free neutrons was unleashed. These neutrons, normally locked away within atomic nuclei, were now free-ranging, flying outward at relativistic speeds. And here's where the cosmic alchemy truly begins. These free neutrons began to smash into other atomic nuclei, rapidly building up heavier and heavier elements through a process known as the rapid neutron capture process, or R process. Think of it like a cosmic assembly line. But instead of adding parts, it's adding neutrons to existing atoms. Each time a neutron is absorbed, the nucleus becomes unstable, eventually decaying into a new, heavier element. This isn't just theoretical. The kilonova explosion from GWI 170817 provided direct observational evidence for this process. The light signature, the spectrum of the fading glow, matched the theoretical predictions for the decay of newly formed heavy elements. Scientists observed the distinct spectral fingerprints of elements like strontium and tellurium, powerful confirmation that elements much heavier than iron were being forged in this cosmic forge. And among those heavy elements, forged in the heart of that kilonova, were the elements that have captivated humanity for millennia: gold and platinum. The aha moment was profound, almost visceral. For centuries, alchemists dreamed of turning lead into gold. They sought to understand the origins of this precious metal, believing it held some mystical power. And for centuries, we've speculated about where the universe's gold came from. Supernovae could create some heavy elements, but not nearly enough to account for the abundance we observe. The mystery persisted. Then came GW 170817. This single, cataclysmic event, 140 million light-years away, provided the answer. Estimates suggest that the kilonova from GW 170817 alone could have generated an astonishing quantity of these precious metals, roughly 10 Earth masses of gold and platinum. Just imagine that, an amount of gold equivalent to 10 entire planets like ours, created in a single fleeting cosmic explosion. So, when you look down at the gold ring on your finger, or admire the gleam of platinum in your electronics, you are not just seeing a beautiful, valuable metal. You are seeing the echo of a universe-shaking event. You're holding in your hand the remnants of a cosmic fireworks display, the tangible legacy of two city-sized stars that spun themselves into oblivion, their final violent embrace seeding the cosmos with the very elements that make up our most cherished possessions. We are quite literally made of and surrounded by the remnants of these cosmic fireworks, the gold that adorns us, the platinum that powers our technology. All of it was forged in the heart of a kilonova, a cataclysmic collision that we can now both hear and see. The realization is more than just a scientific triumph. It's a profound connection to the universe. It tells us that the very atoms that compose us, the elements that make life and civilization possible, have an epic, violent origin story. Our world, our bodies, our jewelry, they are all intimately linked to the most extreme events in the cosmos. We are stardust, yes, but some of that stardust was forged in the fiery heart of a neutron star merger. blasted across the galaxy, and eventually coalesced into our solar system. The advent of multi-messenger astronomy, born from the detection of GW 170817, has fundamentally changed how we approach cosmic mysteries. It's like having a full suite of senses to experience the universe, rather than just one. We no longer just read the book. We listen to the audiobook, watch the movie's adaptation, and even feel the vibrations. It allows us to cross-reference, to verify, to build a far richer and more complete picture of the universe's most dramatic phenomena. The information conveyed by gravitational waves complements the information conveyed by light, each filling in the gaps of the other, painting a complete picture that neither could achieve alone. And this is only the beginning. With each new detection, our ears to the cosmos grow more refined, our understanding deeper. We've heard the colossal collision of black holes, confirming their existence and revealing their sheer abundance. We've witnessed, through both sound and light, the birth of heavy elements in the cataclysmic merger of neutron stars. But what else is out there, waiting for us to listen? Scientists are now pushing the boundaries of what's possible, dreaming of even more sensitive detectors, of space-based observatories that could listen for gravitational waves with frequencies far lower than what LIGO and Virgo can detect. These future instruments could potentially tune into the echoes of the very early universe, the primordial gravitational waves that theoretical models predict were generated in the first fleeting moments after the Big Bang itself. Imagine hearing the actual sound of creation, the universe's first breath, before light even existed to illuminate it. This sensory revolution, this new way of perceiving the universe, is a testament to human ingenuity and our insatiable drive to understand our place in the cosmos. From Einstein's theoretical prediction, a century ago, doubted even by himself, to the painstaking decades-long construction of instruments sensitive enough to detect distortions smaller than a proton, we have finally grown ears to listen. And what we're hearing is a symphony of unparalleled grandeur and violence, a cosmic narrative that is only just beginning to unfold. We are entering an age where the universe no longer just shows us its face. It sings to us, tells us its deepest, most profound stories. It whispers about the birth of black holes, screams about the death of stars, and hums with the creation of the very elements that make up our world and ourselves. And as we continue to listen, what other incredible secrets will the cosmos reveal? What other ancient mysteries will finally be solved, not by looking, but by simply hearing? This is just the beginning of our journey into the sonic universe. There are countless more enigmas waiting to be heard, and we invite you to join us as we continue to explore them, one cosmic whisper at a time. If you found yourself captivated by the universe's symphony, make sure to subscribe to Celestial Enigmas for more journeys into the profound mysteries of space and time. Thank you for listening. We are entering an age where the universe no longer just shows us its face. It sings to us, tells us its deepest, most profound stories. It whispers about the birth of black holes, screams about the death of stars, and hums with the creation of the very elements that make up our world and ourselves. And as we continue to listen, what other incredible secrets will the cosmos reveal? What other ancient mysteries will finally be solved, not by looking, but by simply hearing? This is just the beginning of our journey into the sonic universe. There are countless more enigmas waiting to be heard, and we invite you to join us as we continue to explore them, one cosmic whisper at a time. If you've found yourself captivated by the universe's symphony, make sure to subscribe to Celestial Enigmas for more journeys into the profound mysteries of space and time. Thank you for listening. The journey to hear the universe, to cultivate this new cosmic sense, was a century-long quest, a whisper from the cosmos that took generations of human ingenuity, skepticism, and perseverance to finally amplify into a clear, undeniable sound. We've only just begun to truly listen, to learn the first few powerful notes of this grand cosmic symphony. But what we've heard already has redefined our understanding of existence itself, and the future promises a score of unimaginable complexity and beauty. Remember that iconic chirp, the very first sound you heard, that fleeting, rising tone that marked humanity's auditory awakening to the cosmos? That was the sound of two black holes, one roughly 36 times the mass of our Sun, and the other about 29 solar masses, locked in a death spiral 1.3 billion light-years away. In the final fraction of a second, as they merged into a single colossal black hole, weighing 62 solar masses, an astonishing 3 solar masses of matter were converted directly into pure gravitational wave energy. This wasn't just a powerful event. It was, for that infinitesimal moment, an explosion of energy that briefly outshone the combined light of all the stars in the observable universe. We didn't see it. We heard it. And that hearing, that first delicate perception, wasn't just a scientific triumph. It was a sensory revolution, a profound shift in how we perceive the very fabric of reality. The sheer audacity of this achievement, detecting a ripple in space-time so infinitesimally small, required an instrument that pushed the very boundaries of engineering and physics. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is truly an impossible machine, a testament to human ingenuity against seemingly insurmountable odds. Imagine trying to measure a change in distance equivalent to the width of a human hair over the distance to the nearest star. That's the kind of precision we're talking about. LIGO achieves this by being sensitive enough to detect a distortion in space-time thousands of times smaller than the nucleus of an atom. A staggering 10 to 18 meters across its 4-kilometer arms. Building such a detector meant battling the Earth itself. Every tiny vibration, a distant earthquake, an ocean wave crashing on a shore thousands of miles away, even a truck rumbling down a road miles from the detector, had to be meticulously isolated. The vacuum chambers extending for miles had to be the purest on Earth, preventing even a single stray air molecule from interfering with the laser beams. The mirrors at the end of those arms, polished to an atomic smoothness, had to be suspended with such delicate precision that they would only respond to the most subtle cosmic shivers. It was a painstaking decades-long battle against noise, a quest to create a silence so profound that the universe's faintest whispers could finally break through. The individuals who spearheaded this monumental effort are heroes of our time. Rainer Weiss, whose initial chalk-and-talk conceptualization of a laser interferometer in the 1960s laid the groundwork. Kip Thorne, the theoretical physicist whose profound understanding of general relativity predicted the exact waveforms these cosmic events would produce, giving experimenters a target to aim for. And Buri Barish, the visionary leader who transformed a struggling, ambitious project into a successful global collaboration in the 1990s, steering it through technical hurdles and political skepticism. Their perseverance, alongside a collaboration of over 3,400 scientists from more than 120 institutions across 19 countries, ultimately led to the resounding success of GIBA 15014. They stood on the shoulders of giants, including the controversial pioneer Joseph Weber, who in the 1960s, using his Weber bars, bravely, if unsuccessfully, attempted the first detection, his unreplicable results nonetheless galvanizing the field and spurring the next generation to build better, more sensitive instruments. But the story of gravitational waves begins even earlier, with the mind that first conceived of them, Albert Einstein. In 1916, as a consequence of his revolutionary general theory of relativity, he predicted the existence of these ripples in space-time, traveling at the speed of light. What's truly fascinating, almost ironic, is that even Einstein himself was initially skeptical that their minuscule effects could ever be detected. He even co-authored a flawed paper attempting to disprove their existence, a testament to the immense challenge and almost unbelievable nature of his own prediction. It took nearly a century for humanity to build the ears capable of hearing what Einstein's mind had merely imagined. The first indirect evidence came in 1974 with the Hulse-Taylor binary pulsar. Russell Hulse and Joseph Taylor Jr. observed a pair of neutron stars orbiting each other, and the precise timing of their orbital decay perfectly matched Einstein's predictions for systems losing energy by emitting gravitational waves. This groundbreaking observation earned them the Nobel Prize in Physics in 1993. But it was still an indirect confirmation. The direct detection, the actual hearing, would have to wait. Then came September 14th of 2015. Just days after the newly upgraded advanced LIGO detectors began their first engineering run, a signal arrived, a clear, unmistakable chirp, sweeping up from 35 Hz to 250 Hz in just 0.2 seconds. It was GW150914, the collision of those two black holes 1.3 billion years ago. The public announcement, made on February 11, 2016, ignited a sensory revolution. We had finally grown ears, but this new sense was just the beginning. The discoveries are accelerating, and our global network of detectors is growing, allowing us to hear more, and to hear more precisely. The initial triumph of LIGO was made even more powerful with the addition of the Virgo detector in Italy and later Kagra in Japan. Imagine trying to pinpoint the source of a sound in a vast concert hall with only 2 microphones. It's incredibly difficult. But add a third, and suddenly the location snaps into focus. That's the power of this global collaboration. By using 3 or more detectors separated by thousands of miles, scientists can much more accurately triangulate the source location of a gravitational wave in the sky. This was absolutely crucial for the next monumental discovery, because if GW150914 was the universe's first song, then GW170817 was its first epic opera, complete with fireworks and the creation of gold. On August 17, 2017, LIGO and Virgo detected a gravitational wave signal that lasted for about 100 seconds, originating from a much closer source. The merger of 2 neutron stars, approximately 140 million light-years away, in the galaxy NGC 4993. This wasn't just another gravitational wave detection. It was a watershed moment for science, initiating the era of multi-messenger astronomy. Just 1.7 seconds after the gravitational waves reached Earth, telescopes across the globe detected a short gamma-ray burst, GRB 150817A, coming from the same patch of sky. This confirmed Einstein's prediction that gravitational waves travel at the speed of light. For the first time, we had not only heard a cosmic event, but we had seen its aftermath across the electromagnetic spectrum. 70 observatories around the world, from radio telescopes to X-ray and gamma-ray observatories, pivoted to observe this single event. What they witnessed was a kilonova explosion, a cataclysmic event far more powerful than a standard supernova, yet less energetic than a superluminous supernova. And what did this kilonova reveal? It confirmed one of the universe's deepest, most cherished secrets, where the heavy elements, the very building blocks of our world and ourselves, actually come from. For centuries, alchemists dreamed of turning base metals into gold. This cosmic event, observed through gravitational waves and light, revealed the universe's own alchemy. The collision of these neutron stars, in that unimaginably violent crucible, forged vast quantities of heavy elements, including an estimated 10 Earth masses of gold and platinum. Analysis confirmed the presence of elements like strontium and tellurium, directly implying the formation of even heavier elements like gold and platinum. Every piece of gold jewelry, every speck of platinum on Earth, owes its existence to such an event. A cosmic forging factory operating billions of years ago. We literally heard the universe creating gold. This is the power of our new ears. They don't just detect ripples, they unlock the deepest secrets of cosmic chemistry. And this is truly just the beginning of learning to read the music. We've heard the first few powerful notes of the cosmic symphony, the deep bass of colliding black holes, the percussive crash of merging neutron stars. Now, with new instruments on the ground and in space, we are learning to hear the entire score, from the low, rumbling bass of supermassive black holes to the faint, continuous hum of creation itself. On the ground, the existing LIGO and Virgo detectors continue to be refined, becoming even more sensitive, able to peer further into the cosmic distance and detect fainter signals. Future generations of ground-based detectors are already on the drawing board. Projects like Cosmic Explorer and the Einstein telescope are envisioned as next-generation instruments, with arms tens of kilometers long, pushing the boundaries of sensitivity even further. These colossal observatories will allow us to detect gravitational waves from events billions of light-years away, witnessing the universe's most violent acts as they unfolded in its infancy. They will provide a dense, rich tapestry of cosmic sounds, mapping the distribution and evolution of black holes and neutron stars across cosmic time. But to truly hear the entire symphony, we need to go beyond Earth's seismic rumblings and atmospheric interference. We need to go to space. That's where LISA, the Laser Interferometer Space Antenna, comes in. Unlike LIGO's terrestrial arms, LISA will consist of 3 spacecraft, flying in formation, separated by millions of kilometers, forming a giant triangle in space. These space-based detectors will be sensitive to much lower frequencies of gravitational waves than their ground-based counterparts. While LIGO hears the high-frequency chirps of stellar mass black holes and neutron stars, LISA will tune into the deep, resonant bass notes of the universe. What will LISA hear? It will listen to the mergers of supermassive black holes, those cosmic behemoths that reside at the centers of galaxies, millions or even billions of times the mass of our Sun. Imagine galaxies colliding, their central black holes spiraling inwards over millions of years, eventually merging into an even larger cosmic monster. LISA will track these events, providing unprecedented insights into galaxy evolution and the growth of these colossal engines. It will also listen to the gentle hum of countless binary white dwarfs in our own galaxy, providing a steady, continuous background hum that will teach us about stellar evolution. Gravitational waves offer us a unique window, a way to peer into realms of the universe otherwise entirely inaccessible. Unlike light, which can be absorbed, scattered, or obscured by intervening dust and gas, gravitational waves pass through everything unimpeded. They are the ultimate messengers, carrying pristine information from the most extreme environments and the earliest moments of the cosmos. This unique property holds the key to the ultimate prize, the sound of the Big Bang itself. Imagine trying to see the first moments of the universe with light. You can't. The early universe was a plasma, a dense, opaque fog of charged particles that light couldn't penetrate. The earliest light we can see, the cosmic microwave background, comes from about 380,000 years after the Big Bang, when the universe finally cooled enough to become transparent. But gravitational waves, they were generated in the very first instance of the Big Bang, and they have been traveling across the universe ever since, undisturbed. The dream is to detect this primordial background of gravitational waves, a faint, continuous hum echoing from the moment of creation. It would be the universe's oldest sound, a direct auditory link to the birth of space-time, energy, and matter. It would be the ultimate soundtrack to existence, allowing us to test our cosmological models and unravel the deepest mysteries of how everything began. We've heard the first few clear notes, but to truly understand the cosmic symphony, we need to hear the continuous, unbroken chord of creation itself. The end of the 100-year hunt for gravitational waves was not an end at all. It was the opening of a colossal door to an invisible universe, a universe that has always been speaking to us, but to which we were deaf. The biggest question is no longer can we hear the universe, but what else has it been trying to tell us? With every new detection, every refinement of our instruments, every extension of our sensory reach, we are learning more of its language. We are becoming fluent in the silent roars and gentle whispers of space-time. And as we continue to listen, with our new ears finely tuned, the universe stands ready to unfold its most profound secrets, one unending echo at a time.